let me talk about this one. So this statement right here, I want to talk about. So convergence in probability says this. So for any epsilon greater than 0, we say that probability of A epsilon n so the probability of a typical set, so that is nothing but this set right here, converges to 1 as n goes to infinity. That is the statement, right, that we have. So this one here is nothing but this set, okay? This set is this set by definition, okay? And this statement can be written this way as well. For any epsilon greater than 0, we can, and also delta greater than 0, probability of typical set, okay, because it is converges to 0, we can always find large enough n so that this is true as n greater than n naught, right? So as n is greater than n naught, this is true, okay? So we can always find a large enough n, so this is true for any delta, okay? Because it is converging to 1.0. All right, so having said that, that is another definition of convergence in probability. And when we said delta is equal to epsilon, we can also say that for any epsilon greater than, so I forgot about any epsilon greater than 0, probability of typical set, right? Is greater than 1.1 minus epsilon as n is larger than n0. We can always find such n0 so that this is true. So that is what I said right here. So that is another way of expressing convergence in probability between sample entropy and true entropy. Okay, now let's move to the next page. And then I can talk about these two properties of the typical sets. The first one says the size of the typical set, absolute value of the set, is less than or equal to 2 to the power of nhx plus epsilon. And also with the second one, okay? So there are two properties that we can prove hold. So first one, let's talk about the first one first. So we start with this equality. The sum of all sequences in the set of all possible sequences. So sum of all vector x in the all possible set of sequences and probability of each vector x or each sequence x. So here I use sequence is equal to vector. Okay, so n tuple vector. So x here is x1 the way up to xn, and then there is nothing but x1, x2, xn, and then I use this as x to the power of n because each one of the random variable is IID. So I can say that. So each vector x in script x to the power of n, which is this, okay? And probability of each sequence, okay, should be equal to 1, okay? Because px has to be the distribution, okay? So this must be true. Now, this is a summation over all possible sequences, okay? Now, in the next line, I want to take the summation of x only over the typical set. So, you know, set of all possible sequences can be divided into two mutually exclusive sets. Typical set versus atypical set. Here, I want to take the summation only over the typical set. So this summation could be 1 or smaller than 1. So that's the reason for inequality right here. And then I'll make use of the property of each sequence. The probability of each sequence has to be upper bounded by this one and lower bounded by this one. That's what we have proved. Okay, so each px within the typical set, this is true, right? So for this is for any x in the typical set, for any x in the typical set, we have this. Okay? So I complete it. Okay, so for this one here, px is for x which belongs to the typical set. For such x, the p of x should be lower bounded by this one right here, lower bounded by this one, which is this one right here. So each and every summand in this summation is lower bounded by this number right here, okay, this one. So I have lower bound right here. Since this is not dependent on x anymore, I can bring this outside. So I bring this in front of the summation because that is constant. It is not dependent on vector x anymore. Once I bring it outside, then summation of x over the typical set is nothing but size of the typical set. So I have this finally. So that is the size of the typical set multiplied with this number. So that is the proof for the first one. Okay, so if I move this one to the other side, then I can get rid of the negative sign at the exponent. So it becomes this. So the side of the typical set is upper bounded by this number. All right. Now let's talk about the second property. So for the second property, remember the result in the previous page. What we have said in previous page was for any epsilon greater than 0, we can always find the large enough n so that probability of a epsilon n greater than 1 minus epsilon occurs as n greater than n naught. And um, there exists n naught, such n naught. There exists such n naught. So we can find always large enough n, this convergence occurs for each epsilon. So that is the convergence in probability. So utilizing this result, we can say this is true for any epsilon. And once I have done this, then I can invoke the upper bound in probability of px. Px is upper bounded by this number. Remember that, right? So the probability of typical sequences is nothing but summation of all px, where x is a sequence within the typical set. Okay, so summation over all px over the within the typical set. So probably this one I need to write it again. Let me erase. Right. I am talking about each and every x in the typical set. That is what I mean. Okay. This is vector x. All right. So if we consider this and consider an upper bound, which is this one. So each one is upper bounded by this one. So I can talk about bounded by this number right here. Okay, and since this one is independent of sequence x, so I can write this is equal to, and the number of summation, which is the size of the typical set. Okay. Okay. All right. So that's what is given right here. Okay. So that is the proof of the second line. Okay. Bring this to the other side. So I have this one. Okay. So it sounds great. We talked about asymptotic equipartition property, which will be used again and again in information theory. That is nothing but division of sample space into two parts. So this sample space is a collection of all vector x, right? X belongs to this set, right? And this set can be divided into typical set and atypical set. And each and every sequence of vector x is divided into two. And the typical set, the probability of x is pretty close to 2 to the power of nhx. Okay. And since each one of them are equally probable, the size of the typical set, which is a epsilon n, size of such set is equal to, oh, sorry, I have to have a minus sign here. The size of the typical set should be close to, okay? Give and take away a little bit by epsilon much, okay? So these are the two results, okay? All right, I think the size of the typical set, the probability in the ballpark is close to this number. The size of the typical set is close to this number, okay? Give or take a little bit, okay? So basically that's it for the asymptotic equipartition property. Next time I will talk about examples of typical sets.